Good morning. This session is about designing the combinational logic circuits. In the previous classes, we had discussed about the basic structure of a combinational logic and a sequential logic. In combinational, you have the output defined by the as the function of the inputs, the current inputs, what you have at the input of the combinational block. Whereas in sequential, you have the output determined by the input and also the previous input. That means you have a certain memory aligned with it. And we had looked into the principles of static CMOS circuits, and we had gone for verifying about the pull-up network and the pull-down network structures and how you have the PMOS configuring the pull-up network and the dual structure using NMOS, how they are configuring the pull-down structure also we had studied. And the use of PMOS only and the NMOS only, this also was justified by separate understanding. We will review that once again. And we have also seen the NMOS transistors while getting connected in parallel and in series, how the AND and OR configurations are accomplished, and based on any particular Boolean function, how you can have the NMOS transistors connected. And similarly for the PMOS transistors, how you can have the AND arrangement and OR arrangement. Now let us reason out why only PMOS device is used in the pull-up network and NMOS device in the pull-down network. Now the first case, what you see here is the PMOS device with the source terminal and the drain terminal, and you are giving for getting this device on a logic low here. And as you find at the drain end of this PMOS, whatever be the voltage you have given as VDD, the VDD will be available here when the CL charges fully. Therefore, the VDD without any deterioration will be available. Now let me assume I am putting an NMOS device in the pull-up network and I have a VDD applied to get this device on, and the supply also applied, and this happens to be the drain end and this happens to be the source end, and the output to what a voltage level the CL can have. This is the VDD applied at the drain, and this VDD I have applied at the gate. The moment I have a potential difference of VGS between this gate terminal and the drain terminal, beyond that I am not going to have the VDD reaching to its fullest value, because the moment I reach this, the device would be off. Because here I would be having VDD minus VTH and this would be VDD, the difference would be VTN, which was pulling this device on. But the moment this voltage, for example, if I am working with a 1 volt power supply with a threshold of 0.4 volts, the moment I get 0.6 here with 1 here, the difference would have been 0.4 volt. It is enough to have this device to get on. But the moment I expect this to go beyond 0.6, this 0.4 volts would have to be less than 0.3 or 0.35, at which point of time the device is not supposed to be conducting. So a stage will never come wherein you will have the output voltage to reach VDD. That is the reason why, though using a NMOS device at the top and a PMOS device at the bottom can give a good buffer instead of an inverter, the output voltage is never going to be, if I have this levels reached, it's never going to be fully VDD, it's never going to be fully zero, as I am going to discuss for the pull down case, assuming a PMOS is connected at the pull down network. We will continue with that. Now coming down to the pull down network, I normally use an NMOS device. And once again the reason is going to be the capacitance. If it fully discharges, I should have a conducting path here, and I give a VDD here, and the gate to source voltage is always going to be the VGS with this at 0 volt. Therefore there is not going to be any dearth of any drop in voltage there, and I will have a pakka 0 logic at the output. So the PMOS device is giving a pakka 1 logic at the output, and the NMOS device is giving a pakka 0 at the output. if I go for replacing the NMOS device what we had discussed here with the PMOS device, what could happen? In order to get this device PMOS on with the terminals drain and source here as per the potentials I need to apply for the 3 terminals, assuming the 3 terminals. Now I will have this device on to get the discharging accomplished only as long as this VGS voltage is maintained within the levels. And once again here, the moment I have the absolute value of VTP is reached, below that value I am never going to have this device keeping itself in on condition. That means I am stuck up in this case only with the VTP instead of a 0 level. Whereas here I am stuck up with VDD minus VTN and the low level would now be VTP. So this reason makes you have the NMOS devices are in the pull down network and PMOS devices in the pull up network normally. Now the properties of complementary CMOS gates, once again we have discussed this very well so far. That is, the CMOS with a Pakka VDD level and a Pakka 0 level is able to provide a good noise margin, a good high noise margin and a good low level noise margins also. And theoretically speaking, you don't have any static power consumption because we have the condition that when the NMOS device is on, the PMOS is never on, and when the other case also. And we are assuming the device is not leaking any current at all. The properties of complementary CMOS gates as a snapshot, what we will have very high noise margins with a very good logic 1 level and a logic 0 level you assume, and you have no static power consumption. We assume ideal devices with no static current leakages and all, and assuming once again only PMOS devices at a time conduct and only NMOS devices at a time conduct, we are not going to be having any short circuit or rail to rail current also flowing in any steady state mode. And during switching, actually we have discussed before how you have the short circuit current, short circuit power getting dissipated and how short circuit current was flowing, that we have discussed already, and comparable rise and fall times. And we are going to be able to size the devices also. These are the general properties what you have got to remember, and the advantages what you have when we use the pull up network and pull down network as we have discussed in CMOS, the full rail to rail swing, and because of that very good noise margins, and you call these devices ratioless. Actually, we are going to be talking about the PMOS and NMOS devices with 2.5 to 3 times ratio and all that, but we still call this as ratioless. The main reason is what? Irrespective of whatever be the size you get, you are going to have the output nodes charging to VDD and the output nodes discharging down to ground. This level is never going to be changing, though you may have the time taken to be like this if the load is very big, or like this if the capacity load is very small, and even for the pull down, this one also like this, very delayed or very early, still early and all you may have, but you are never going to have any other voltage level other than your VDD and 0 volts. Therefore these are called ratioless. But the raise time, fall time and all are going to be changing based on the time constant what you are going to be having. R happens to be the device resistance Rn or Rp and the CL. Now there always exists a steady state path between the output node to VDD or the output node to ground. Therefore, at no point of time you have any node in floating condition. This is the biggest advantage what you have in these circuits. This floating output node, because it is not available there, you are not finding the circuits very vulnerable to other effects such as crosstalk, leakages and all this interference and all. And you have the taking into account the output impedance, you have either the path to VDD or ground, therefore very low output impedance, and with the gate, ideally speaking, you have a pakka insulator between the gate and channel generated, so you have the maximum input resistance, theoretically infinity, but though it's not going to be same because you are talking of the order of angstrom size of thicknesses for the gate material, the silicon dioxide material, and you are actually having theoretically no direct path between the VDD and ground unless you consider during the switching, as we discussed about the short circuit power dissipation, and no static power dissipation, no leakage current components. And the propagation delay solely depends on the load capacitance and resistance of transistors. I mean, why of the transistors? When the output node is getting charged, you have the NMOS pulled up devices configuring, that is sending your current. They make the current to flow, and during the time of discharging, you have this from the load, the current discharging down. So at that point of time we will consider Rn, at this point of time we consider during charging the Rp resistances, and the CL, whatever be the load capacitances, they remain here. Now the next big understanding what you need to have is, if I have a digital circuit configured using PMOS and NMOS devices, how very simply we could go for modeling the circuit as a switch delay model, because we will need to find out the propagation delay, we need to find out the TP-LH and the TP HL, and all these propagation delay characteristics ultimately, as I told you, is dependent on your resistance of the device and the load capacitance. And the resistance of the device means how many devices I have in the pull-up network and what configuration of transistors you have, and how many in the pull-down and what configuration. All these determine the value of R. And CL, we assume only the load capacitance there, but you are going to be having, based on the number of devices what you have connected, even internal nodal capacitances. How they are going to be playing a role, you will understand in this part of the chapter. Now we are assuming a 2-input NAND gate here. In this 2-input NAND gate, naturally one device B and another device A, they are connected in series, and you have the same PMOS devices for the same, that is the dual network, you have them in parallel. Now with this structure, what I am showing you here is, for each device you depict the resistance of the device as Rn and another Rn here, with a switch which is controlled by the logic state what you have. Similarly here Rp in series with the switch. So this will be connected when you have A bar true, that means when you give a logic low. Similarly B bar will be true when you have a 0 given here. Therefore you have these two devices either conducting to get this CL fully charged, or only one device conducting through this. What I mean to say is, you can have the current flow through this like this when you have the output node reaching high, and you may have this device instead conducting, or both the devices also conducting. Therefore the R configuration at the top, and you have on the other hand one device here. If I go for shorting this with a logic 1 here because it's a NMOS device, and I give a 0 here, I am not going to be having this NMOS on, then I am not going to be finding any discharging path. And similarly, when you have 1 given here, this would be shorted, whereas this device is not going to be on. With this device on, maybe I will have whatever nodal charge I had in this internal capacitance, this will go down to the ground. Now, how you have the inverter compared with this? Let us see. You have for an inverter only one PMOS device at the top and another NMOS device at the bottom. And if I am talking about an R2 gate, naturally 2 PMOS devices in series and 2 NMOS devices in parallel. Just the complementary structure what you had for the NAND arrangement. If it is a 3-input NAND gate, naturally you are going to be having, as I told you, 3 devices in the pull down network in series. And this is going to be controlled by A, this would be B, this would be C. And similarly for the pull-up network, you would have 3 PMOS devices connected like that in parallel, and all would to be connected with your VDD. And herein I have my ground and this output node you are taking. And here I have got my A bar signal, here I have my B bar signal, here I have my C bar signal. Now I will have internal capacitances as I showed you before. This is one internal capacitance, this is another internal capacitance. What I will have here as the complete load capacitance at this point. When I talk about this nodal the load capacitance CL, what is this due to? This CL can be due to if I connect fan out here, whatever be the number of fan out devices I connect, assuming CG of both the PMOS and NMOS equal, I may have 2 CG if I go for only one inverter connected, or based on 10 inverters if I connect into 10 I will have. So that is how you define the fan out, the capacitance due to the fan out. In addition, what are the other capacitive components you will have? This we have discussed many times. You have the wire interconnect, whatever you have contributing for some capacitance value. So the wire interconnect resistance and capacitance, about this we will study in detail in a later chapter. Presently you just remember you have another component of CW which is due to the wire capacitance, and then most importantly the other parasitic capacitive components whatever you have due to the devices connected at this point. For example, the drain to bulk, the diffusion capacitance of this device, the diffusion capacitance of this device, whether they are on or off, based on that the overlap capacitance effect and the diffusion capacitance of this and the overlap capacitance, all these capacitances are getting added to the load capacitance what we identify as CL. Whereas if I look at this capacitance what I have in between, this is due to the source terminal of this device and the drain terminal of this device. This node is generated. Therefore, whatever be the diffusion capacitances due to these, those things would be added here. Therefore, we have got to remember something. While drawing the layout, this being the diffusion, I can draw the poly like this. So, whatever the technology allows you to leave the space in between the devices, you very stringently, very calculatedly you have got to have good layout practice generated. Because whatever capacitance I have generated are in this area, what are the capacitances? Even that is, if I look at this structure, you have the area capacitance and perimeter capacitance of this source terminal and the drain terminal. If they are both connected in series without any metal interconnection in between, the capacitance here, normally we assume they are divided into two. That is, half of that belong to this device and half of that belong to the bottom device. That's how we assume. So here the parasitic capacitance is due to the area and peripheral capacitances as defined in the model 5, and how big, how wide a diffusion layer you are taking and how wide you are taking your poly layer, and what difference in space between these two, what distance you create between these two. All these actually define how much of internal nodal capacitances are there. And all the while when you draw this layout, you have got to remember to use the technology rules and whatever be the allowed space and all in between the layers of the same type or different types, you have got to be very stringently following. Therefore, this should give you a brief idea about what is configured, what are the components configuring your CL, and what are the capacitive components configuring your internal load capacitances and all. Now with that, now we will go for discussing about the effect of what input patterns we have for the inputs, what we take for the gates. Here it is said the delay is dependent on the pattern of inputs. How is it going to be? Now let us take different conditions from 0, 0, 0, 1, 1, 0 and to 1, 1. Now when both are zeros, when A and B are zeros, these two inputs are going to be active, which will make both the PMOS devices to conduct, and I will have a faster charging of the capacitive load. And in such a case, both these devices are going to be half naturally. And the effective resistance, because I am having two devices on, this is going to be Rn by 2. Sorry, the effective resistance what will be offered is going to be Rp by 2. Now we will go for the next case when I have a 0 for this and a 1 for this. In such a case, with 0 for this PMOS device, this path would be on, and with a 1 here, this would be off. Now I have only one path. In this case, I am going to be having only Rp as the load, Rp as the resistance, and your CL is going to be there. So previously the delay was dependent on 0.69 times Rp by 2 into CL. When one of the inputs goes low, I have got the timing to be as per 0.69 into Rp into CL. And similarly, when I go for considering this sort of a case, with the present case of conditions, I have been considering so far only the load capacitance CL. What other effect also is to be considered is the CINT capacitance. We had taken the case of a 1 here and a 0 and a 1. Now the charging current flows like this, charging the CL, and we find even this transistor also is on, the B device also is on, which makes the CINT also get charged. Therefore, if we calculate the timing taken for the output to raise from 0 to the maximum, I will have additional time what the current takes to charge even the CINT. Over and above the time what is needed for CL, I will have time for CINT also. Now this is one point. Another point what we will have is, if this is 0, if this happened to be a 0 and this happened to be a 1, this is going to be off and this would be on with a 0 applied here, then the charging would be only for this. So based on whether it is a 0 1 or 1 0, whether only the CL is charging or along with CINT also is charging, we have different timings. That is the second case what we will consider. The next case would be, I have put here the conditions, the discussion. It went only for low to high transition. What I have here, that is taking your output to be presently low and it goes towards high logic state as discussed here. And let us take the condition of the high to low transition, the TP-HL. This was TP-LH case. Now what will happen through the TP-H to L case? Let us take combinations. I have both to be ones, both were off, and whatever I have here will be discharged, whatever I have here will be discharged. Now this condition I will now impose. Previously I was having a 0 state for this switch B transistor, and it now is going towards logic 1. In such a case, previously because this was 0, this device was off and there is no chance that there will be any charge here on this CINT. Even if there was charge, because this device A happens to be on, I would have had, when this was 0, this whatever charge I had charged it down to the ground. Therefore, the timing which is going to be taken by the circuit, the logic gate, to get to 0 from the logic 1 here through these two resistors are going to be comparatively less than another situation what we will take up now. Previously it was 1 and this was 0. Because this was 0, when I was charging up this node for a logic 1, this CL was charging, and because this is making this device on, I have even this capacitor to have been charged. Therefore, in this condition, when I consider the Tp H2L, it would so happen naturally that the charge whatever I have here should go through here when this goes to 1, and similarly whatever charge I have here also will go down to the ground. Through this you will have the current flowing. Therefore, now I will find more time for both the capacitors to charge, and only if this was the thing to charge down to 0, then it would be less time. So these effects are now shown in the form of the simulation, the output of the simulations here. The first case is when I have both and A and B to be ones which are becoming zeros. Therefore, the output naturally has to go high. That is, we have both. We consider the case when both A and B are previously ones and they go to 0. Now I will have this to be working and this also to be working, and these two devices are going to be off. Now the next condition is when I have A is equal to 1, the green condition, when A is equal to 1 and B goes from 1 to 0. A was 1 and B goes from 1 to 0. Therefore, only B starts conducting. With A1, this would be on, whereas this would be off. So, the charging will happen only for the capacitive node CL. This CINT will not be charged because this device stays off only. Therefore, I have lesser time taken, but since I am having only one path for the current to flow, I have a delayed version of this green line, what you see. Now we go for taking another case wherein I have A is equal to 1 to 0 and B going for only 1, that's constant 1. Now this makes this to be on and A from 1 it goes to 0, so this device is off. At this point of time, I will find the current going through this to charge CL, and I also find the B device conducting. Therefore, I have current going through this charging this one also. Therefore, you take even more time to raise up because the capacitive loads are added up and I have only one path of conducting PMOS. These delay patterns, these delay dependence on the input patterns is thus very important, and you have got to understand it properly. The same gate, the same 2 input NAND gate will now be taken from the perspective of the pull down network. I previously had A and B both to be of 0 value. Now the logic is 1 at the 2 inputs. In such a case, it is taking this sort of a VTC. And in this case, because both were 0 and now only they are getting on, the charging, that is the discharging, will now happen only from load capacitance down to the ground. The next case is when B happens to be 1 and A happens to go from 0 to 1. Now because the B happens to be 1, previous charge whatever was there might have got discharged, and now you have A to be going from 0 to 1, and this paves way for the charge from here to go down also. The third case is when you have the other way around. A was 1 and remains at 1, and B happens to be going from 0 to 1. In such a case, with this transistor already on, when this CL was charged, we would have had even this to have been charged because this short here is there and CNT will be charging too. Now when this happens, both this capacitor should discharge and this also should discharge, and that is why you have this sort of a transition, the VTC, is shaped like this. It further moves down towards the left. That means I have a weaker pull-up network, and this way naturally when we go, we mean that your pull-up network is weaker. The next idea would be design of fast complex gates. The first design technique, a few design techniques we will study here. Assume I have a pull down network of n inputs. We had seen before that TPHL is going to be determined by the sum of all the RC components of the path. It's going to be proportional to that. In this case, I have the load capacitance CL and the charge on CL passing through all the n resistance offered by all the n devices. Similarly, so for the other capacitors, for example C1, whatever charge I have, it will pass through M1, and C2, it will pass through M2 and M1, C3 will pass through all these three. Like that, ultimately, as you can realize, the device in one, the M1 is going to be actually carrying all the currents. This has to pay for n values of n different currents, whereas this M2 device would be carrying all the currents which are getting discharged from C2, C3 up to CL. So this way, if I look at the devices with equal sizes, if I do, they are going to be carrying different current values. Instead, the M1 with its position of carrying the maximally possible current, I can make this much bigger during the layout, and M2 with somewhat reduced current, because I am not going to have the C1 current going through that, so somewhat a reduced shape for size, the width for M2, and similarly for M3 I can still some more reduction I can do. So this way I can go for progressively sizing. These progressively sizing devices from Mn to Mn can go for making the circuits drive faster. The next one would be the transistor ordering. I have got 3 inputs considered here, and I have out of the 3 inputs, the input in 1, which is actually shown to be changing from 0 to 1, is a frequently changing one, frequently switching device, and these 2 I assume are always 1. With this structure, when I go for using the pull-up network, what I will be having here, whenever I go for, because my input is 0 to 1, it crosses. Previously with the 0 input, I would have charged the CL fully, and I would have charged with this permanent 1 on here, I would have charged C2 and I would have charged C1 also. Therefore, the TPHL delay is now going to be determined by the discharging time of all the charges what I have here, here and here. In addition to that, you consider I have the pull-up network which is going to be charging not only CL, it's going to be charging C2 and it's going to be charging C1 also. So the TPL to H also is going to be more. This actually, therefore we can say the delay is determined by the time to discharge all the 3 capacitors and the charging and discharging both, as explained now. Now assume I keep the in1 connected to M3, which is connected to the output node. That is, it is closer to output node. If I keep this input here, if this was 1 and this also was 1 before, I would have just had this grounded and this also grounded. With this 0 and 1, I would not be having so much of effect, like the same explanation we will give here. through this pull-up, if this was 0 before, I would have been charging only this, and I would not have charged C2 and C1 because this device is off. There is no path for that to flow. And once again, when this goes up from 0 to 1, this M3 device, I would be discharging only from CL term because I would have already had C2 and C1 discharged completely. So this is going to be in effect, making the rise time and fall time faster. So the transistor ordering is a very good technique. The next one would be, I have some alternate logic structures here. A big structure, we have already discussed about this. We have around n number of inputs. Instead of keeping an n input NAND gate, it is always advisable to go for lower fan-in gates. We have also seen how the fan-in is going to be creating the self-loading effect, how it is going to be increasing the time delay. So it is always to search for, to imagine alternate logic structures which would go for giving in reduced delay timings. The fourth design technique would be about isolate the high load capacitance what are to be driven by the gate what I have through the use of buffers in between. This is two inverters connected alternately. You form a buffer, I can say. Now this buffer arrangement isolates the high load capacitance from this. This itself is already a 4 input NAND gate, so its internal capacitance also would be more. And in addition, if I go for giving a high load capacitance, naturally I am going to be having the gate suffering from high fan in and also high fan out. Therefore, it is better you go for removing the fan in from the fan out, the high fan in gates from the high fan out load supply. And the fifth design technique would be, we know the energy dissipation totally is CVDD square. Now, if I go for operating the circuit using VDD, and if I go for making my swing to be only instead of VDD, V swing, the reduced voltage swing, then I would be having the power dissipation determined only by the V swing square, which is less than your VDD, which will go for in turn reducing the energy and the power dissipation. But we have to accept the fact that this will make the gates operating slowly. So far the ideas about some good fast complex gate designing techniques we have seen, and we have also considered the CMOS circuit arrangements and all. The next one would be, we have studied about individual gates and what the sizing would be we had seen. If I go for taking an ALU, the ALU which is going to be driven by stages of modules of circuits of consisting which are internally of gates, how am I going to consider the sizing of such a circuit? I have a circuit, it may have a number of stages, and each stage may in itself have a number of set of gates, and how am I going to be connecting such set of gates, and what sizing consideration am I going to be making, and what is going to be the final load at the end of, for example, a microprocessor or an ALU load what I have shown here, a data path, and what internal, the first stage input gate capacitance is going to be, how efficiently I am going to run this sort of a system. We will see from here on. Yeah, we will go for considering the logical effort calculation and all. Now, as we discussed before, how to go for calculating the delay of the logic gate. Inherently, you have the delay which drives the delay incurred due to driving its own intrinsic load, and the delay incurred due to driving the additional load. Therefore, what I do, I have my gate delay defined as the delay whatever my circuit is incurring due to the intrinsic capacitances what you have, and the effort delay. What gates I drive, how many such gates I drive. In the last page I told you. What did I tell you? The logical effort and the fan out loads. I may drive a complex gate, or I may drive 4 such complex gates. Therefore, the effort delay is going to be called as your H parameter, and this parameter is now going to be F into G. How many fan outs I have and what is the logical effort. And this F is going to be what? The fan out, your C out by C, which you already know, which we did for the inverter also. Okay. With this in mind, we would now go for identifying how to calculate each of these components. The first one would be what? The logical effort. The logical effort, very simply said, you can read all these things later. Whenever I have an inverter, a basic PMOS I have got, a basic NMOS I have. So the logical effort of an inverter with twice the size of N for the PMOS, right? That's how we had. So whatever be the delay incurred due to the inverter drive would be your TP0, I told you. And similarly, when I go for considering some other complex gate, how big is it in comparison with an inverter? We are going to check. Okay, an inverter with twice the width for PMOS, 1 time the width for NMOS, I am taking as the unit gate. And in comparison with our inverter, how big is my other gates are going to be? Because I should have the delay derived only based on the G whatever I calculate, here in turn the H what I calculate. In addition to the fan out capacitance and the initial input capacitance what I have as the C1. Right? Now, we will go for considering the logical effort calculation. I have my inverter with twice the width, the numbers indicate twice W and 1 W here. My input A is the fan in that now drives my 2 gate capacitances here and 1 gate capacitance here. So it's going to be 3 Cg, or I will just put only 3. Whereas here I now go for what gate? It's a 2 input NAND gate. How do I size? I want to have effective 1 here and an effective 2 there. So how did I size it? Since 2 transistors are in series, I made this as twice the width and this also as twice the width. So 2W plus 2W, and what I have here, either this can conduct or this can conduct, therefore I will leave only 2 for that. So all the devices are now sized 2. Identify that properly. Okay, now I go for calculating. I take 1 fan in input, A input I take. How much of capacitance does it need to drive here? 2. How much is it needed to drive here? Another 2. So it is what? 2 plus 2, 4. Whereas here this A was in a position to drive only 3. Whereas here I am driving 4. So 4 by 3. The ratio between whatever be the additional bigger load what you have for the complex gate divided by your inverter input gate capacitance. That is what is your logical effort. So the logical effort for a 2 input NAND gate would be this. If I go for asking you to calculate the logical effort of a 3 input NAND, how will you do? I would go for having what? 3 NMOS devices in series. What would be the size? Yeah, I will have 3, 3 and 3, and here what will I have? It would be 1. Here I will be 2, 2 and 2. Correct? Anyone can drive. The best case delay only we calculate. Okay. So I will now have, if I call this as A, B, C, A will now have what? 2 here plus another 2, 3. Another 3 there. So it is 5. So the logical effort of a 3 input NAND gate would be 5 by 3. And if I go for calculating in the same way for a NOR gate, what I do? If I go for 2 input NOR gate, I myself have given 2 input NOR gate, what is there? I size it as one here and another one here, and here I should have 2 devices in series. It should have been 2, so I increase that, so 4 and 4. So for each input, if I go for taking either A or B, I take, not both, correct? So what is the effort? 4 needed here and 1 needed here, so 5 by 3. Understand it? Whereas here it was what? 4 by 3. And you go for calculating for a 3 input NOR gate. In addition, you will have another transistor here. Then the size will be what? Instead of 4 here, 3 devices. So you will have what? And I will have another 1 input for C. And this input will be C with the PMOS here. So the size would be what? 6, 6, 6. Therefore for 1 input, 7 by 3. Whereas 5 by 3 it was for NAND gate. This is another reason, this is another way how you can explain why NAND gates are preferred over NOR gates. In addition to the other reasons, how we conceptually explain with respect to the number of devices whatever you have and all that. So the logical effort calculation you would go for taking in this manner. Okay. Yes. And here this is the logical effort with respect to the number of fan outs. What does this signify? The fan in, he says. Why? Because the inherent delay, what it will incur by its own structure. Okay, its intrinsic delay, that would be this. And for TP inverter, this one, for TP NAND gate, a higher load, so an higher inherent delay, and then it goes for increasing more steeply than your inverter, naturally. And similarly, so far for NOR gate, it would still be worse. Okay, all these you can go for configuring, and that is you can go for constructing and finding out the delay and all you can do. And one of the assignments is going to be this way, it would be. So I have given here anyway, intrinsic delay and effort delay. Why I call this as effort delay? Its own intrinsic delay is its own capacitance getting charged, and because of that whatever be the delay incurred. Whereas the other output loads, what I go for connecting in terms of the other combinational gates. And I calculate the logical effort for such gates. And I go for counting how many fan outs I am going to be having. So G times F, I go for doing it. That many complex gates, with each gate having a particular amount of logical effort. This way, if you do a chain of combinational gates, if you have, you can go for naturally calculating how much delay it is going to be incurring. How are you going to size the devices also? Understand? So the logical effort of 2 input NAND, 3 input NAND and n input NAND. Now, so far we were talking about what? Its inverter and its own inherent delay, intrinsic delay we had discussed, and sizing PMOS, NMOS we discussed. Then what did we have? Get this inverter made bigger for a more complex gate. And when I go for a complex gate, instead of one P and one N device, you are going to be having more number of P devices and more number of N devices, equal numbers. And based on that, I said you will have its own internal delay formed. And we also discussed about the fan outs. We just took only one part and fan outs. Now I say I take my logical input across cascades of modules. The first level of cascade is there, its output is taken and it is given to n number of the second stage of the cascade. Now in this process, my charging the nodes would be the current what I give for my one path, another path, and second path and a third path. For each of the paths, based on their own their own gate capacitances, I will have to be sending current for charging. So in such a case, I have got to consider the branching effort also. You understand? I go for taking a 64-bit data and I work out of the 64-bit data a particular path I have, and for that path I want to calculate across one gate flow. One bit I am taking, how the one bit transits through from the input side to the output side I need to take. So in such a case, I will go for taking into account this path, and also while driving my path which is under consideration, I should also take into consideration the other paths which were driven. So I need to take into account the branching effort. So what current, this is the path what I consider, how many other such paths I have driven on the way, I need to consider. So branching effort if I go for taking, because I need to size this device not only taking into account this path, I should take into account the other path sizes also. So the branching now will come into the picture. So the branching effort, how do I define it? Its own path, the C on path plus the other paths what I have, off path, divided by the C on path. This is what is going to be the branching efforts. Now more I have number of branches, then I will have B value to be more. If I have B value to be more, I have got to size up my devices accordingly. Whether I consider an inverter or I consider any complex gate. Understand? So if I have a multi-stage networks, we were talking about what? Only one stage. When I talk about branching, naturally I am taking into account a number of stages where branching occurs. Now the delay is going to be its own intrinsic delay for a particular Pi, if I have the ith stage. And for that, what is the logical effort? How much is the fan out load? And in this, the stage effort, okay, how much is that? Gi times Fi. Fi means what? I am driving the Fi plus 1 and this is driven by Fi minus 1 stage. Okay, and like in the inverter, if I am considering a 1000 femtofarad load, I said you will have the first inverter with a driving capability of 10 and the second inverter with another 10, the third inverter with another 10. That way I will be driving easily with 1 femtofarad internal load capacitance. I will be able to drive my 1000 femtofarad in 3 stages. And how to calculate the number of stages also we had identified for an inverter. The same way we can go for doing it for a complex set of gates also. That is where we are now arriving at. Previously we had only one inverter. So we just took only its own TPO we considered and we never bothered about the other things at all. And if I had the same inverter with so many fan outs, I would have done the same thing. Okay, now what are the things what you need to study here? The stage effort Hi is equivalent to Gi into Fi, and the stage efforts for each stage. As I told now, the first stage effort it is, the second stage effort, all the stage efforts for effective operation. Why did I take 10, 10, 10? Because the sizing would be whatever be the ratio times the previous. The next one would be whatever be the ratio times the previous one. The same ratio we maintain. That is how you go for configuring with the same raise time and fall time. Okay, without disturbing the raise time and fall time. The same way I go for doing this. The path electrical effort. What is electrical effort? Previously it was just F. I now have the final load capacitance divided by its internal capacitance. The path logical effort is what? For each gate in each stage, I have G. Okay, now I am having in my path whatever I take, G1 to be the capacitive load of, the logical effort of present gate, G2 is the next gate, G3 is the next gate. So the product of all is going to be your path logical effort. And similarly the branching effort, capital B. And the path effort, what I now define as the product of all these, G times F times B. Okay, and now what would be the path delay? The delay incurred, the sum of all these PI and the sum of your path efforts. Okay, now we are going towards a stage where you have cascades, and in each stage you have complex gates, and all the complex gates have their own logical efforts, and all these stages, total logical effort, how much is it, total path effort, how much is it, which is taking into account what is the output bigger load to be driven. For example, your off-chip bus. Okay. So the optimum effort per stage, how do you calculate? In the same way as we did for my inverter, the effort power n, this is going to be the number of stages what you will configure is equal to h. So h is nth root of capital H. So the minimum path delay would be this. It is the same just like how we had before. Additionally, I am putting your Cj. That is due to the delay incurred by a complex gate compared against that of an inverter. Okay. So the sizing factor, how do I now do? As we did for the same inverter, what do you take? The sizing for individual gates. I size each and every subsequent gate S times bigger, because I am putting what? The path efforts for each stage is gradually increasing, right? Now I will have the S to be the size factor for each gate, so derive them from front to end or the other way, any way you can. So the input capacitance of CG1, the input capacitance CG1 is what? G1 into S1 into C reference. What is your reference capacitor? And the next capacitance CG2 is going to be how bigger? It has to drive a bigger load F1, and what is going to be the branching? B1, this many times higher. If I am going to be having branching some 2, 3, I would have what? CG2 to be so much. Okay, and the branching effort Bj you go for calculating. With all these things, I can now define G2 S2 C ref is equal to whatever be your F1 by B1 times G1 S1 C ref. You understand what it is? I have my first stage. My second stage is going to be so many times bigger. This B1 will go here, and F1 G1 S1 into C ref would be equal to this. I am driving a bigger load with a structure which is involving a lower capacitance. I subsequently go for increasing the drive strength. So at any stage I, Si will be equal to this. The product factor of Fj by Bj for j is equal to 1 to I minus 1. I leave the first stage out. Now what does this G1, G2 and all signify? The logical effort. And the sizing I should take accordingly. If I am given with such a gate structure, such a circuit structure, what I have? An inverter 1 driving one of the inputs of a 3-input NAND whose output is driving one of the inputs of a 2-input NOR and another inverter, and I have given what? The CL, and I have given what? The intrinsic input capacitance. How much is it? Now how do you go for sizing all this? Now my aim is what? To drive a 5 load capacitance, 5 farad, and I am having one here. How do I size this? The size A, B, C we have taken. We have to find out the value of A, B and C. Now what is my first aim? Number of stages. What do I have? How many stages I have? 4 stages I have. The first stage with a size of 1. In proportion to that, how much should be A? In proportion to A, how much should be B? How much should be C? And this, how efficiently it will drive the 5 farad. Now the time delay, the TP is going to be what? The sum of individual delays and individual equations, expressions I have, and I sum everything. That's what is giving me TP. And individually when I look at what do I get? I have for each the delay factor, and for each I have the fan out load factor. For each I have the logical effort, and gamma I assume 1. So the minimum delay through the path determines what? Each stage should bear the same gate effort. Same gate effort means what? Fg. F1 G1 should be equal to F2 G2. Should be equal to Fn Gn. Right? With this basic guidelines, what do I now have? F1 G1 Fg is equal for all the stages. With that in mind, we now calculate the path logical effort. G is what? The product of all these Gi, and the path effective fan out is what? The effective final load capacitance divided by the first one, and then the branching effort is what? On path plus off path by on path. That we have assumed 1 for in our case, but if it is different, I will go for having the product of all these, and the total path effort, what I said was H is equal to GFB. The same thing what we had discussed. It's time. It is 55. Oh, you have got to go there. Okay, right. So I will give you this problem. You can follow this. I will upload this material today. Okay, I will upload this material. You refer to that. And how many of you absent? 4, 8, 12. All are present today. Correct?